So in this video, we're going to start with an example problem. This is from a modified example problem from your book. We're going to go ahead and go through some of the basics behind a control strategy without necessarily getting into a lot of specifics. So reading the problem as stated, it says a system is specified to have a cut-in speed of 5 meters per second, a cutout speed of 35 meters per second, and a rated generator input of 7.5 kilowatts per meter squared. The maximum power coefficient is 0.5. Determine and plot the following for both the system with no controls and the system controlled to meet the constraints. We're going to go ahead and we're going to just basically plot out what the power density of the system should be. So again, this problem statement goes ahead and it specifies that it has a power coefficient of 0.5, a cut-in speed of 5 meters per second, a cutout speed of 35 meters per second, and a power density of 7.5 kilowatts per meter squared of actuator area. So I'm going to go ahead and I'm going to do a plot, but for wind velocities ranging from 0, let's say, to 50 meters per second, right way beyond the cutout speed. Our power density is going to be 0.5 times the power coefficient, times rho wind velocity cubed. So that is basically what the uncontrolled power density would be. For the controlled power density, again, we're going to split this up into several regimes. We're going to start that, so for a power density of 0 would be for when the velocity, the wind velocity, is less than the cut-in. And we're also going to say that the power density is 0 for when the velocity is greater than cut out. The power extracted would be the maximum power density if the power coming in is greater than the power of the air is greater than the maximum power of the system. And then what I'm going to end up with is, for the rest of the time, my power is going to equal the power density based on the power coefficient, for a constant power coefficient. So these are my control. This is my control strategy, and this is my uncontrolled strategy. If we were to go ahead and plot them together, this graph shows power density on the y-axis and wind speed on the x-axis. You can see, starting at cut-in, that my uncontrolled I have a constant increase based on velocity to the third power of power coming in. But for the controlled strategy, during my constant power coefficient stage, I'm again following basically the same curve as the uncontrolled scheme, right? So that is during this regime. Then what's happening is that now the power coming in is greater than the maximum power rated for the generator. So now I have constant power extracted. So again, that would be this regime. And then when the velocity gets greater than 35 meters per second, I completely cut out and my power is 0. Again, you can kind of see the same kind of graph, but in the power coefficient versus wind speed graph. Again, nothing until 5 meters per second, then constant power coefficient until I hit a point to where the power coming in is greater than the generated power capacity of the generating power capacity of the generator. And then at this point, my power coefficient goes down because it's equal again to the power extracted, which is constant, divided by the power in the air, which is increasing with wind speed. And then when I hit 35 meters per second, it cuts out altogether. If I look my energy density in terms of kilowatt hours per year versus wind speed, you can see that the controlled strategy has less power, of course, extracted overall as compared to the uncontrolled strategy. But again, the controlled strategy is safety concerns and costs in terms of sizing the generator for what would be the using the distribution functions. You would basically size a generator for the wind speeds that occur the most. So it wouldn't be the maximum wind speed, it'd be for wind speed lower than the maximum wind speed in the area. Something else interesting to note, here are some graphs. These are actually from your book, and it's looking at some data from a 850 kilowatt wind turbine generator. So it's its output response to wind speed variations. This is actually from the manufacturer's website. So you can see here, you have basically wind speed per time, right? And you can see how varying it is. And then you have here the generator speed variation, the speed and RPM of the generator over time, right? Again, very variant. So here's the pitch angle, right? The pitch angle, which basically adjusts for these varying wind speeds. You can see the pitch angle, the blades changing over time. The point is to be able to get this. The control strategy is meant to be able to have a constant power extraction, right? So control theory or control application is huge in the area of wind power. One other thing I want to cover is just the concept of a wind farm. Now, you have a homework problem on this. So wind farms, as you can tell, wind farms are just basically an area of land, a plot of land that just has wind turbines spread out across it. When sizing a wind farm, it's important to know that, right, you have to have a certain amount of spacing in between the wind turbines. If they're too close, the wind speed reduction from one wind turbine would affect the performance of another. So the general rule of thumb is that it's recommended that there be a space of 2 to 4 rotor diameters prevailing the wind, facing the prevailing wind, and 8 to 12 rotor diameters parallel to the wind. So again, this would be the wind direction, 2 to 4 across, and then 8 to 12 diameters in the direction of the wind. The remainder of these slides are basically just some manufacturer or examples of commercial wind turbines. This one is a 1.5 General Electric energy wind turbine. You can see the different models here across the top of the table, and they categorize them according to their specifics. So rated capacity, cut-in speed, cut-out speed, rated wind speed, and so forth. You can also get, obviously, performance plots. This is its kilowatt performance in kilowatts versus wind speed in meters per second, and you can see each of their performance curves accordingly. This is an example of the one we were just looking at earlier with the control strategy, the 150 kilowatt Vestas wind turbine. Again, this is the same turbine that we were looking at these graphs for, the Vestas V52. And again, you can see the rated capacity, you can see their cut-in and cut-out speed, their rated wind speed, rotor diameter, sweep areas, and so forth. Again, another plot of its power versus wind speed. Here you have another example of Berge 10 kilowatt wind turbine, and again, it's rated according to its capacity, cut-in, cut-out speed, rated wind speed, rotor diameter, and so forth. And here is an example of its power output versus wind speed. This particular turbine would be considered the cheaper end in 2006, ranging from $20,000 to $25,000. Thank you very much. This slide concludes the final video for the chapter on wind turbines.